because they're physically different in shape, you can't always use it to predict the exact angles between, but you can use them to get a pretty good idea. Also, VSEPR doesn't work for transition metals. Whenever you have multiple bonds and angles, realize that the more bonds there are, the greater the electron density is. So if you were to look at this particular bond right here between these carbons, you would predict it to be 109.5 based on the fact that it's tetrahedral. But then if you were to look, there's a lot of electron density here. So because this molecule, it could actually push some of these bonds further away because there's a lot of electrons there. The greater repulsive force could create greater bond angles even when it appears like it should be a tetrahedral molecule. Another thing for large molecules, whenever you look at large molecules, they have more than one central atom. You can't talk about the geometry of the entire molecule. Instead, you talk about the geometry of each central atom. So you'd say, okay, here's carbon number one. Carbon number one should be tetrahedral. Here's nitrogen. Nitrogen number one should be tetrahedral. When I look at carbon number two, it should be trigonal planar, and so forth and so forth and so forth. You can't talk about the geometry of the molecule as a whole if it has more than one central atom. So we want to review polarity. Remember, polarity of the molecule is affected by the polarity of each bond and by the geometry of the molecule. So in these particular molecules that we see here, there's a partial positive and a partial negative for each one of the charges. Now, if you were to look at the polarity as a whole, it's a nonpolar molecule. And the reason why it's nonpolar is because you can have a line of symmetry. And the line of symmetry, the line of symmetry says for every pull this way, there's a pull this way. For every pull this way, there's a pull that way, and they cancel each other out. So you've got to be aware of looking for lines of symmetry. Now, if you want to classify each bond as polar or nonpolar, now in order to do this, you would look at the change in electronegativity. Okay, so the bond right here between these two tends to be classified as nonpolar. So that means this is nonpolar and this is nonpolar. Now, the difference between carbon and oxygen is sufficient where it could be classified as a polar bond. So we're going to classify that as a polar bond. And oxygen and hydrogen could be classified as a polar bond. So if you were to look at it, we've classified all the bonds here as polar or nonpolar. Now, the last thing that you want to do is you want to look at the molecule as a whole. And you'd have to say, is there any symmetry between these? Yeah, this hydrogen cancels this one, but this oxygen and hydrogen are no longer capable of canceling each other out. So you would see that there's a net pull of the electrons towards this way, and so you would say this is a partial negative side of the molecule, which would of course make this the partial positive side of the molecule. So whenever you look at the molecular polarity determines the solubility of a molecule as well as the reactivity of the molecule whenever you're looking at the nucleophile. So this right here is a nucleophile. Nu, it's not an element. It's saying that it's something that's negatively charged that wants to attract to a positive sort of molecule, a positive part of a molecule. And so if you look and see right here, this right here is a halogen. Okay, it's just any halogen, chlorine, iodine, something like that. And if you were to look, the nucleophile can actually attack this carbon right here because this is pulling the electron so much that it has a partial negative charge. That means this thing has a partial positive. So this negative charge can attract to that, and what happens then is it kicks off the electrons from the bond onto this, and now you've released the halogen and you've attached the nucleophile to this particular element. You can see how this mechanism or this reactivity could be very useful to chemists who are trying to build molecules given certain substituents. Valence bond theory. Valence bond theory, we're talking about as two atoms overlap, their orbitals overlap. So for example, when you have two hydrogens, remember these hydrogens are in the 1s orbitals. So I have a 1s orbital and I have a 1s orbital. Well, when those two overlap, instead of creating two 1s overlapping orbitals, you can say that they create what's called the hybrid orbital. So whenever you have, for example, these two overlap, it's an s and a p orbital, it's actually called an sp orbital. Okay, this is generally still called an S and this is still called a P, but you have an overlap that creates these hybrid orbitals. Now, whenever you overlap in bonding, remember that you don't want them to be too close, you don't want them to be too far. You want them to get to the point where it's the maximum attraction between the two. So the maximum attraction and repulsion. You don't want them to be so close together that the nucleuses repel, and you don't want them to be so far apart that they're not attracted. You want this minimum potential energy. Remember, nature is always trying to minimize energy. Okay, so that's why it reaches this level and it bonds there. Be aware of that. So this is a general guideline for you to follow, that nature is always trying to decrease the amount of energy. So we create what are called hybrid orbitals. If you were to look, you have the ground state of beryllium. The ground state of beryllium is this 1s, 2s, and then there's nothing in the p. And then you have the excited state of beryllium, which is 1s, and then we've promoted one of the electrons from the 1s to the 2p. Now this is possible because there's actually a very small energy difference between the 2s and the 2p. It's still there, but the amount of energy required to promote an electron to the next level is very, very, very small, and can be occurred just by a collision between molecules. Okay, there's very, very little energy required to do that. So this actually allows us to say, remember when we said Be would bond to Cl2, and it looks like it's satisfied right here? Well, the energy difference between these is so small that energy is actually saved by promoting the electron to the next level and forming two bonds with something else. Okay, that's actually more stable. Another example of this is carbon. Now, when we talked about the Lewis dot structure of carbon, most people tend to draw it like this because it has 4 valence electrons. But remember, the ground state, the lowest energy state of carbon, is one in which you have 2 electrons that are there, and then 1 electron there, 1 electron there. So really, you're promoting an electron to the next level whenever you're trying to form 4 bonds. Okay, before we go forward, what we will discuss is a model. Okay, this is a model that works, and you're going to be taught it in chemistry and in college chemistry, but there's zero experimental evidence for this particular model. It works mathematically, but we have yet to find any sort of verifiable physical evidence of it. And that's hybrid orbitals. So the overlap of an s and p results in a new, what we call, molecular orbital that we call an sp hybrid orbital. Okay, so you can create these hybrid orbitals from the combination of various orbitals between the two things that bond. Now, the assumption is that when you combine these two shapes, you get a new shape that we predict to be called the hybrid orbital. Now, there's something called an sp3 hybrid orbital. And an sp3 hybrid orbital is what happens with carbon, because carbon can form 4 bonds with four different hydrogen atoms, and so as a result, it's a combination of carbon's s and 3 of carbon's p orbitals together to form the hydrogen orbitals. So to make all of these energy levels equal, or all of these bonds equal, you have what's called a hybrid orbital as opposed to an s and an s overlapping, and then a p and an s. What happens is it creates a hybrid orbital which makes all of them the same energy. What about whenever we're bonding to 2 things? An example of this would be with nitrogen, or whenever carbon has a double bond. Because of the hybrid structure, this right here is still considered to be a single hybrid structure. So when carbon forms bonds with 3 bonds, this right here is bonded to 3 things. So I'm using my s, and I'm using 2 p orbitals to create what's called a hybrid orbital. That's why it's called an sp2 hybridization. Next, we call the sp hybridization, and if you notice, carbon's forming a bond with an s and a p, which makes it an sp hybrid. So the reason why these hybrid orbitals are possible is because it creates an average orbital between the two as opposed to what we saw before. So here's the energy level of the s orbital, and here's the energy level of the p orbital, and this is over dramatic. It's actually not much different. But whenever you do this, in creating a hybrid orbital, what you're doing is you're basically creating an average orbital that it makes all 4 energy levels equal. Now, if you notice, it's more towards the p orbital because there's 1, 2, 3 p suborbitals and only 1 s suborbital. So it's not going to be in the middle, it's going to be skewed towards the 2p orbital. So as a result of this, you have 1 electron each in the sp3. This is an example of what you see with carbon. Carbon has 4 electrons, 1 in each of the sp3 orbitals, which allows it to form 4 equal bonds. You see the same thing with whenever we talk about beryllium. Beryllium promotes one of its electrons from the, it has a 1, 2s, and then 1 in the 2p, and it can promote those electrons to make an sp orbital.